Good morning, everyone. Hopefully the rainy start to the day hasn't dampened your enthusiasm for the day's events. It looks like a wonderful schedule. And I'm going to start off with some discussion of some cybersecurity myths and the problems that they engender. The idea behind this talk is something that's been building during my career. I've been working in cybersecurity for really over 40 years. And during that time, I've had a chance to observe successes and failures and misconceptions along the way. Last year, along with my two co-authors, we started exchanging ideas about things that we heard that we had run across that were myths, that we were somewhat surprised still existed in the field. And we ended up writing a book about it. And it's been well received in a number of quarters. I'll tell you more about that in a little bit. It's been added to the cybersecurity canon of essential literature just recently. And I found that some of the topics are worth talking about to groups. And so that's the genesis of this talk. I'll just mention here this wonderful illustration on the first slide. Is by the illustrator of the book, who happened to, we were able to get a really good deal because she's married to me. So she's sitting up here at the front. Let me talk about cybersecurity as a field. All right, so if you think about a field like, let's say, physics or chemistry or medicine, the question is, how did it become a field? How do we know it's a field? Well, it turns out that there's some common characteristics to defining a field of endeavor, a field of study, a field of practice. And part of it is based on history, that you have things that everybody within the field point to as important moments in the history, or that we can identify that those are associated with the field. There's an accepted body of knowledge that the majority of people are expected to know and to follow. If you make a reference to it, everybody goes, oh yeah. So for instance, in medicine, if you refer to Gray's Anatomy, people may not have read it, and it's a little, or not Gray's Anatomy, but well, that shows I don't do medicine. Whatever, the book, but whatever you refer to, and they sort of recognize that. Let's say physics. You refer to Newton's works. People recognize that as part of physics. There's some generally accepted references and standards in the field, common terminology that everyone uses. But until those things fully develop, to explain what happens in that field of endeavor, people develop superstitions and myths and explanations that are often based on limited observation and are found not to be completely correct. And that's where we are in cybersecurity. So I'll start by saying, for history, cybersecurity isn't new in a sense that some of us might use new, but as a field, it's really quite new, because we could argue that the first articulation of some of the principles occurred in the mid-1960s and showed up in the Ware report, Willis Ware's report in 1967, that was done at the behest of the Air Force. Then Project Multics came along in 1969 to explore issues of not only operating systems and architecture, but primarily the funding was to discover how to do secure multi-party computing. The follow-on to the Ware report by Jim Anderson and company, that was done for DARPA, was called the Anderson Report. And then I think most of us, those first three, many of you may not have run into, but it's worth going back and finding them, by the way. The Trusted Computer System Evaluation Criteria, we've heard of the Orange Book, some of us have read it, and there was the Red Book, the Yellow Book, the Green Book, the Brown Book, and some others that set forth some basic principles and architecture for trusted computing. So we have history, but it only goes back really 75 years at most. So it's a new field if we compare it to almost any other field of engineering or scientific endeavor. So history, okay, we have some history. Standard and common references and terminology, yeah, we definitely have that. So not everybody agrees what should be part of the common body of knowledge. We have several versions of it. So ISACA has one, ISSA has one. The British Standards Organization has the SIBOC. ISC squared tests against one. So we have a number of different, but they largely overlap. We have a number of standards as to what's considered to be good practice or things to watch for. And many of these come out of NIST. NIST does some great work, so if you're not familiar with them, it's worth looking at some of those standards. But I'm assuming you all are, particularly the 800 series. And again, some of the professional organizations like ISACA, ISSA, ISC squared, the British Standards Organization, ISO, and others. We have some standard textbooks that we all tend to know about if we don't actually have copies on our shelves or on our disk or cloud storage. Matt Bishop's Security and Computing, for instance, or Computer Security, Flieger's Security and Computing, Bellavin and Cheswick's Firewalls book, and Ross Anderson's Security Engineering, and so on. We also have some common terms of art that mean something special to us that would mean something different to a different kind of audience. So for instance, if we use the term ransomware, that's not used in any other field. It's specific to ours. And if we use the term virus, we're referring to something very different than what the biologists and doctors and others would refer to as a virus. We also have some other things like ROP. It's an acronym that's become a noun for return-oriented programming and side channel attacks and other kinds of terms. So going back to that list of what makes a field, we can check off several of them. But we also have myths. And there's a lot, but I'm only going to address 4 general myths that we have as a field, some of which some of you may still cling to a little bit, and one common misconception that leads us into difficulties. So I'll start with the first one, and if you look at that, and I say it's a myth that we have a clear definition of cybersecurity, that sort of calls into question what we all do. If we don't know what cybersecurity is, well, what is it we're doing? That's something that I suspect we're often asked by our supervisors. What are you doing? And in this case, it's trying to explain what cybersecurity is. So let me start by saying, all right, let's look at a definition of cybersecurity and see why it may not be adequate. Let's start with this one, which is an intuitive definition, and I think most of us might embrace this if we had to explain it to someone. And we'd say that cybersecurity is something where we work on computing systems, and our goal is to protect against all kinds of threats to those computing systems. That seems like a reasonable first cut at a definition. Well, let's give some thought to this as to what this really means. So, for most of us, as we secure our systems, can we protect against random hackers? Which is not a good term, but I'm using it here. And the answer is, yeah, we could probably do that. Most random individuals don't have the sophistication to overcome the defenses that we put in place. So yeah, we can do that. How about malware? There it's probably the case. Most malware have some limited vectors that they use, limited behaviors. We can protect against that. Good, check there. How about nation-state adversaries? Here we fall down on this. And this is because some of the nation-state adversaries that we may be facing are very well-resourced, very talented, very persistent, and they can outspend us and spend more time and effort on attacking us than we can spend protecting. So I would contend that it is unlikely that too many people here in the audience would be up to protecting against nation-state hackers. So here we begin to run into problems in protecting systems. Well, that's not a problem with the definition. That's a problem more with adversaries. So let's explore the definition a little further. Can we protect against the UFO invasion? Again, I think the majority of the people here, no. If you're Jeff Goldblum with a MacBook, maybe. But we don't know anything really about any threat vector there. We don't know what they might exploit. They may have capabilities and tools beyond our understanding. Probably do. Maybe if there were a postulated attack, maybe they have telepathy, and then passwords are definitely passé. So we can't really say anything about this. And yes, some of you are going, well, there are no UFOs, there are no aliens. Clearly you haven't been on X, on Twitter, because they're posting there for sure. Elon Musk may be one. Can we protect against an extinction-level meteor impact? No. That's something that's going to be beyond any of our capabilities. This is the definitive denial of service attack. We're kind of out of luck here. But if you're creative and you're thinking, what can we do to protect? What are we going to do? Well, what we can do is we'll establish colonies on Mars. And we'll have a data center there, and we can store all of our memes and cat videos, and they'll be safe. Right? I mean, that sounds like a reasonable idea. That's a way for continuity of operations. Hot spares are a really good idea. But if we explore that hot spare idea, eventually the sun is going to devolve, burn up enough hydrogen, it's going to turn into a red giant, and it will consume the inner planets, including our backup sites. So, all right, there's another threat we have to worry about. Admittedly, it's a few billion years from now, so it's probably not within our budget cycle, but it's something that we can't protect against. And you're probably thinking, okay, well, by then we can go to other places in space, we can set up other locations, but then we have the heat death of the universe to worry about. And so, ultimately, we're going to lose out on being able to protect our systems. These illustrate a couple issues related to cybersecurity that are worth mentioning. First of all, the definition isn't really helpful for us because it doesn't allow us to anticipate attacks and defenses very well. It doesn't tell us the scope of what we need to protect. It does illustrate, first of all, that security is more of a process than it is a goal, because changing elements of time where new things emerge as threats or new things emerge as defenses changes our security posture. So one of the first aspects of myth is really held generally by managers, supervisors, others who believe that security is a state, and once we achieve it, we just have to maintain it. And that's not correct. It also illustrates that good security, in some sense, is an economic process, not simply a technical one. Because as the kinds of threats we're protecting against evolve in scope and sophistication in some cases, it's going to cost us more and more to protect against those threats. And we can never protect against all threats. We can spend an arbitrary amount of money and never protect against all threats. So let's make another attempt. And here I'll hearken back to some work that was done in the 1980s and approach this as a job of system design rather than talking about protecting against threats. And I'll do this to illustrate some other aspects of definition. So back in the 70s and 80s, we looked at the idea of how do we define security, and we said we will define security according to specifications. And the specifications will be formulated with respect to a security policy, like Bell-LaPadula or the BIBA policy or some other kind of policy. And we will specify that there are safe states for a system to operate in. If it's in one of those states, all's good. And as the system executes, it changes state. We have transitions from one state to another, and this harkens back to perhaps your algorithms classes of long ago, talking about state transitions. But really, that's how things work. Every time the program counter ticks over, we have a new set of states of registers and what's in place. And as long as that new state is within the allowed states, the system is safe or it's secure. This implies that there are bad states. And yeah, I could make a joke here about West Virginia for my wife, but I won't do that. We have bad states that the program can transition into those states. And we want to avoid that because those don't follow the policy. They're not part of the specification. We especially don't want to remain within them because the idea that we have, if we follow this definition, is that we have that system specification of behavior of what we want the program to do. And if it executes in a way that is outside the specification, we call that a fault. And colloquially, we call it a bug, but fault is the formal term. And that can result in a failure if we end up in a state that we never leave. That's a bad state. And a failure in a protected system is a security failure. And yes, for those of you who are wondering here, in the 70s and 80s, the work that was done in defining security along these lines actually was one of the drivers of software engineering development. We also have, and we know this from practice, undefined states. We don't specifically define them as good states. We don't specifically define them as bad states. They're simply undefined. And often these are unanticipated. Entering into one of those states is an error, but it's not necessarily a fault. It's a problem to enter one of those states because we don't know what's going to happen. Maybe it'll be safe, maybe it won't, we don't know. It's possible that we can transition into one of those unknown states and then back to an okay state. And that might be okay, as long as it's in a transitory element in those unknown states and doesn't actually lead to any failures, then maybe that's okay. The problem is this space looks something like this, where the undefined states are huge. And we may not have a complete definition of the bad states. This requires that we have a complete specification of the good states. So there's an assumption here that we can specify what's good, we can specify what's bad, and we have some knowledge of everything else. But as software, as systems get more complex, the total state space explodes. It explodes. It's at least a polynomial explosion, if you remember that, or if you've ever run into that, or possibly even exponential, depending on the number of variables. Well, it's not supposed to be blank. But, so here's the problem. Most of what you're using today operates in an undefined state space because it's never been defined what it should be. Have any of you ever heard of or seen a full specification of, well, let's say Word, Excel, Oracle DB, or anything that's in free software? They just don't exist. Full specification is almost never done anymore. Folks at Amazon and Google are going back to doing this for their internal systems because they see the value for it. But the software that we interact with, we don't have those specifications. And in part, it's because it's time-consuming to produce them, which means it's expensive because you have to have people trained to do it, you have to have the tools, the expertise, the software, and therefore most organizations don't do this. We also generally don't teach this because companies don't demand that of our graduates. Our graduates, or people who write software, just want to write code. They don't want to write specifications that don't execute. They want to write the code and include Easter eggs in the code, which is, of course, part of the problem. We only have, in fact, general requirements from which to derive the specifications. In most cases, we do not have a complete list of what we want the program, the software, the system, whatever it is, to do and not to do. So as a result, we can't really define correct. This has been an issue that's been known for a long time. One of my favorite quotes is, a program that has not been specified cannot be incorrect, it can only be surprising. That's the realm in which we operate. We do not actually work on building and maintaining systems to be correct and secure. We maintain them to minimize surprise. And the surprise is because we don't really know what everything has been built to do and not to do. We are imposing our own requirements on top of what somebody else has constructed in most cases. This cartoon, I love this one too, right? It was just going to be a laser printer before we started adding features. This is what a lot of software development from vendors gives us as they do new releases. And this is also something that results from agile development processes. Why? Because none of those processes are designed to trim the existing software. They're to add new features or fix features, and it's always adding to rather than subtracting from. So everything we have gets more complex, and complexity is part of the problem, as I'll talk about shortly. So that example illustrates some of the difficulty with another definition of security that we can't achieve. And this has been recognized for a long time, that the field started off in the formal sense by study in government and academia and others. We started off talking about security, realized we could never completely define it or achieve it, so we started talking about trusted systems. And that's where the Orange Book and the Rainbow series came from, as trusted computing. And then we went to, well, we don't even know for sure how to build trusted systems, so let's talk about how we do trustworthy systems that could be trusted if we understand what we wanted to trust them to do. And then we decided, well, even that idea of trust is kind of nebulous, so we'll talk about resilient systems, that if something does go wrong, because we can't anticipate it all, it's easy to come back into operation. And even that turned out to be pretty difficult, so now we talk about risk. Now we measure the risk of things. And a lot of our focus is on what to do after a problem occurs, not to prevent it. Without this clear definition of security, we don't have metrics. We don't know how to measure security. We can't compare two systems. Now, if you were to take the same base system, go out to the vendors that are out here, install their applications or their processes on those systems, and then you try to compare them against each other to say which is more secure, you have no metrics. They have their metric. It's, they made money for selling their version, so obviously it's better for them, but that doesn't mean it's necessarily better in any application area. We have no metrics. Or how about safety or privacy, which are related concepts? How do those fit into any definition of security? Again, we don't have one. So as a result of this, we have a lot of folk wisdom around the idea of security as to what it means. As I just indicated, we don't have a good definition. I mentioned NIST as kind of an exemplar of setting good standards. NIST actually has 3 formal definitions of cybersecurity. So you can pick the one you like. I don't think, that's not very good as a standard definition, but that's where that is. As I said, a good definition would help drive our designs and operation because we would know what we're operating towards. We would know what values, what features we would want to use. It would enhance our communication with each other and with management. It would help support development of better tools to achieve that end. But we don't have that. Now, I've given this talk in places and people go, oh, we've got a definition of security. It's confidentiality, integrity, and availability. Well, you start working in the field for very long and you realize those aren't good definitions. First of all, they're not clearly defined. You can't measure them. What's 3 more units of confidentiality? there's no way to determine that. And it doesn't include everything else that we would want to have when we think about that generic definition of cybersecurity. There are other features that we want to have, like authenticity. Authenticity isn't really one of those three properties. So we don't really have something that's even close. Let me move on and talk about others, because I want to be sure I have enough time to get through these. A second myth that is common to many of us who have a technology background is that more technology is better. We've got problems, okay, let's put on something else, some other security feature. And that's why currently a study that came out a couple years ago from Gartner said that your average large enterprise is running 57 different security products by different vendors. 57. Now, I would say, looking at this, why aren't the base systems incorporating the safeguards so that we don't need to do that? That's like buying a car and having to install your own brakes. There's something wrong with that picture. But a good part of this problem is that as technologists, we don't value simplicity enough. Now, we know we can't define and design software very well, but we keep adding new things to old platforms, and the complexity is killing us. Systems get bigger, not smaller, as a rule. If you look at Microsoft Windows, which a lot of you probably have to do on a day-to-day basis, if you dive down inside, you can find an interface for every version of Windows that Microsoft has ever produced. You can go all the way back, not only through Windows, but to DOS. You can eventually find yourself at a DOS prompt and can run DOS programs in the current version of Windows. Why? Legacy. They have customers that depend on still being able to run their old software. And it's not just Microsoft, not to pick on them exclusively, but our financial system, we have things that are running on emulators that are emulating emulators of old Burroughs and IBM systems, and those emulations are in place because the financial software is running in COBOL. And for it to run, it needs to have 2 or 3 generations of emulators of old mainframes that were produced in the 70s. Our financial system is running on that. Your bank accounts, your loans, your stock trades are running on multiple layers of emulators. We continue to go to support legacy. We don't know how to do it well, so we just build more layers on top. And when a layer fails to work properly, well, we put it in a container and put it out in the cloud in a virtual machine. That doesn't make it simpler. When I graduated from grad school, and you know, I usually throw in here that was learning on coal-fired computers back then. I could take on a class and explain to students anything that happened in a computing environment from the circuit level to the human interface, because I had learned that all for the systems of the time. There's no person alive who can do that with current systems. They are so complex, they have gotten so complicated that no one person can master that entire stack, which means, in part, no one is able to do systems level thinking, no one is able to really identify all the seams where problems occur, and that complexity is part of the problem. So we're kind of stuck in a loop where we have broken software that we're using. We need faster hardware to execute it. We get faster hardware, and now it's capable of running another layer of complexity on top of the software that was broken in the first place, which is why we have to have 57 different products installed to take care of all of the difficulties. That also leads us to avoid investigating some very specific new approaches that might be useful. So there are, for instance, new approaches that we could use in operating systems or architecture if we weren't supporting all of that legacy. But we don't do it because it isn't economical. It isn't going to support that. It's only in niche markets that we have some of those new mechanisms, which actually are much better. How many here have ever heard of Green Hills Integrity, for instance? Anybody? Wow. Usually there's someone. You should be thankful that it's there because it's run on a lot of flight control and nuclear power systems. It is a formally verified real-time operating system. It is extraordinarily robust, very well protected, meets the Orange Book standards of an A system and the common criteria systems of TCL 7. It's also extraordinarily expensive because of all the effort and time they put into it, which is probably why you haven't heard about it. You're not going to run that at a small business or a university because of the cost. But it's very, very resilient and robust. That's part of the issue. People don't want to pay for better quality. It leads us to things like this. And you know, I said I wasn't going to pick solely on Microsoft, and I'm not intending to necessarily say bad things about the Wenger Corporation here. The upper left there is sort of a typical, what we'd call Swiss Army knife, with a little logo there of the Wenger Corporation in Switzerland. The picture on the right is an actual product that Wenger makes and sells. So if you're looking for an interesting stocking stuffer for the holidays, probably the use of any stocking that this is stuffed into is as a weapon in a melee. But this is an example of what happens with a lot of our systems. We just keep adding new tools. Now, none of those are useless. I would contend that you could probably build a small house with that item on the right. You'd skin your knuckles a lot and curse creatively quite a bit, and the output, the product, might not be as good as what other artisans could produce using tools designed for purpose. But that's the issue. A lot of what we're doing with our tools are not designed for purpose, and they don't work as well, and they bring with them their own vulnerabilities and limitations. So if we have a new IoT system, what are we going to run on it? Oh, well, we'll download Android or Windows and use that. But that means we're taking all of the functionality and all of the flaws and all of the other history and capabilities that we may not need in whatever device we're going to load this onto. So that's part of the problem, is we continue to accrete tools rather than to build for purpose. And then the bottom picture is something someone suggested to me as a metaphor for current software, where we start off with some very simple ideas, and then we end up interweaving them and getting them all intertangled with each other so we can't separate them out anymore. We can't remove one because it's so tangled with the others. But if you've had some background in EE or physics or just painful experience, you know that when you start jumbling wires together, you end up with interesting EMF effects with induced signals and added inductive resistance. And so as a result, things don't behave as you expect them to, as if they were simple, straightforward wires. Enough of the metaphors there, but the point is that complexity leads to failures. It leads to emergent failures, where it's more than just the sum of the weaknesses or issues within the software. It's at least the product. The idea of emergent failures has been around for 30 years. It's been written about by many authors, and if you're interested, there's an author by the name of Charles Perrow, who is now deceased. He used to teach at Princeton, and his last book several years ago was called The Coming Catastrophe, and it was about the internet, about our networks and our systems getting so complex we could no longer anticipate failure modes from something unusual that might happen. If he had written that after this rise in large language model AI systems, I think he would have added several more chapters to point out some of the issues there. We're using these things in ways that are safety or security critical, and we have no idea how they interact with each other or where the faults possibly are. Because when we pass the point of understanding a system and modeling it, we can't be assured of the outcomes. We're depending on faith. That's the kind of thing we're sort of shooting an arrow into the air, and we don't know where it's going to land. We just hope it isn't on top of somebody. And that's what we're doing with software, and it's not a good way to be. And that ties into myth 3, that technology is the solution to these problems. What are we going to do when we have a problem? We're going to write another program to solve it. Well, that, I would contend, is not the best approach. Now, those of us who work in the field are very focused on the technology because we have all of these threats that we have to deal with. And some of them are very complex with a lot of data. We look at malware, and we want to build IDS systems, and we have firewalls in place. But what we're failing to understand as we build and deploy these solutions is not everybody has our technology background. Not everybody has the awareness of the technology that we do. Bob Courtney. How many of you ever heard of Bob Courtney? Anybody here? No. Okay. Well, again, this goes back to the history of the field, not being aware of some of the early experts in the field. Bob was the first security expert for IBM. He started IBM's path down a lot of what they were doing in security. And he has 3 laws. You can find them online. Courtney's 3rd law is there's no technical solutions to management problems, but there are management solutions to technical problems. And a really clear example of where we try to do that, for instance, is with people clicking on links in email. We don't have some really strong technical solutions, so instead we try to educate, incentivize, and threaten our user population with not clicking on links in email, which of course doesn't work all that well, but it's resorting to a management solution because the technical solutions just aren't there. That's a very trivial example, but there are more. The issue here is that when we design the technology, we are failing to consider the range of people that are involved in the solutions. We tend to design for our peers and not the general public. We fail to understand the limitations of the downstream users in what we build, and then we blame them when things go wrong. You may say, well, no, we don't blame them. Well, I'll give you 2 examples of where as a field we have. A few years ago, thankfully it's died out, but we would post these stories of people, for instance, with the desktop tower system. They would use the CD tray as a coffee holder, or where they were supposed to point the mouse and click, and so they'd pick it up and clicking at the screen, and we label these as dumb user stories. That's not funny. That's actually an indictment of how we design things and how poorly we trained the end users. It's sad, actually, but that's an example. And if any of you have ever repeated, the user is the weakest link, that's exactly what we're talking about. Because users can actually be part of the strongest link if we train them appropriately, and I'll get to that in a moment. But where we're failing to give proper consideration is how well are we designing systems, software and hardware, for people with physical limitations? People whose eyesight is poor or non-existent. People who may not be able to hear audio signals. Using color coding on the screen when we have people with color blindness. Having fine mouse movements, and then we have people who have essential tremor or Parkinson's or some other kind of issue. They can't use those systems. We're not thinking about them. An aging population. I'm becoming more aware of that as time goes on. Some of our abilities for vision, for contrast, for being able to see what's there, and just, of course, the endurance to get through all of the spam, it decreases with age. What are we doing with systems to try to take into account that range of users? Or people with different biometric profiles. There's a wonderful film online I think you can see for free if you go look for it. It's called Coded Bias. And it's about a young woman's realization. She's a student at MIT. She was a black woman and discovered that facial recognition systems simply didn't work on her. Why? Because it was a bunch of older white men who had programmed the system and trained it. And they had trained it on largely male white faces. And as a result, the system didn't do well for biometrics for people with other racial characteristics for facial features. This is not uncommon. This shows up in a lot of other places. But it's an unconscious bias of not building for the general population. And even there, if we want to have an international market, there are cues in different languages. There are words, there are colors, there are things that we would represent on the screen that mean different things to different populations. And if we fail to take that into account, we're going to limit our market or have things used the wrong way. We've probably all heard the story of, at least I think maybe it's too old, about why the Chevy Nova didn't sell well in Spanish-speaking countries. Is because Nova means doesn't move. That's an example of a cultural bias that wasn't thought about carefully as people were looking at things. And then there's differences in literacy. If you look at the worldwide population, the majority of people are not literate in whatever language is local to where they live. And sadly, in the US, something like 50% of the population can only read at the 4th grade level. So why are we designing things that require perhaps an undergraduate's ability to understand terminology and error messages and instructions on the screen? So all of this contributes that we're not taking end users into account. And they're not the weakest link if we educate them, if we give them simplified and appropriate interfaces, that if we don't make them do things that we could easily automate. Another thing for those of you who have environments where you have to worry is having non-punitive reporting of problems is critical for better security. If you create an environment where somebody clicks on a link by mistake and they're afraid to report it because they're afraid of some punishment, you've just made them part of the problem. Because you're not going to learn about it. They're going to pretend it didn't happen. They're going to go on their merry way. If instead you create an environment where users are educated and they're part of the system, and they feel confident and they know who to immediately call up and say, I goofed up, I clicked on the link, you need to check my system, now they're part of the security posture. Users, the end users, are not the enemy. They should be part of the system, and we should build our systems accordingly, because people are always going to be part of the computing environment until our robot overlords take over, and then we don't have to worry about it. But that's going to be a ways away, I hope. Myth 4, patching is somehow security. Patching is probably a bane to many of us. I know it is to me. But building it the first time is the right way to do things, not after. Patching after something happens is a failure that we're now remediating. Think about any other field. Oh, the plane crashed, but we know how to fix it. Here, roll this out. That's a disaster. That's not security. That's not quality. That's true of pretty much anywhere else. But we have been conditioned by vendors to believe that their ability to roll out patches on a regular basis is somehow a measure of good security and quality for their product. That's just wrong. We have been conditioned to accept failure as somehow a feature. We've got to get away from that. But what's happened is by conditioning us to do that, as a marketplace, we don't demand quality. We aren't willing to pay for quality. We aren't willing to wait for quality. And as a result, we continue to get things that aren't quality. And the more things get patched, the more complex they get. This is, again, a metaphor. I can't show you software, but inside a lot of your software products, this is effectively what it is. You have long-time software engineers who are scared to death to have to go in and make a change because they don't know what will break. It continues to accrete patches, and that's a really bad way to design and run critical software. We have to get away from the idea that fixing something after the fact is somehow making something better. Richard Donzik, who was Secretary of the Navy, had a conversation with him, and he brought up this wonderful analogy. He said it was kind of like the Ptolemy versus Copernicus issue in astronomy. So for those of you who don't remember back that far, my good friend Ptolemy, his view of the solar system is that everything revolved around the Earth. And when you were going to do navigation, you used what's called an affirmus, a table of the position of the stars and the planets. And you would think that would be kind of simple to do, but predicting things like observing where Mercury is in the sky, because if you believe that the Earth is at the center and Mercury is somehow traveling through the sky around the Earth, there are occasions where Mercury appears to go backwards. That's Mercury retrograde, for those of you who read the astrology pages, and hopefully you don't, but that's how you have to explain it, is that the planets sometimes go backwards, because that's your model of the universe, where everything goes around the Earth. That was the Ptolemaic view of astronomy and the universe. And then Copernicus came along and said, no, wait, maybe the Earth isn't at the center. Maybe the sun is, and things go around the sun. And look, all these odd things we were talking about go away, because we can have a very clear definition of what this is. And in return, Copernicus and some of his followers were spurned, were vilified, were imprisoned, and a couple were actually put to death because they dared to question that the Earth was not at the center of all things. But Copernicus was right, and follow-on observations, and it led to, for instance, some of the things that Galileo developed, and that all of what we have today is modern cosmology, because he dared question that underlying fundamental principle. We're still at the point of the Ptolemaic view of software engineering, that patching is the right way and that adding complexity is the right way. And we need to have a revolution to say, no, that isn't the right way. I've sort of beaten that one up enough. Let me move on to this misconception. And we've gotten this misconception that speed and cost are the most important factors. Certainly our management seems to think those are the important factors. But I would ask you to really have some thought, some deep thought for at least a few minutes. Why is time to market more important than quality? Why is the first thing available more important than something that's safe and well-designed? In software. Now, most other markets, that's not the case. If you rush something out that's defective, you get penalized. Lawsuits, government regulations, and others. But in the software arena, it's speed. And not only speed to market, but speed of operation. Why is a faster system better than a safe one? Why is it that we're told not to include preconditions, postconditions, assertions, checks on range of variables, because it will slow something down? Someone has made the determination that speed is more important than quality. And why is ease of patching more important than developing something correct in the first place? Which goes back to what I was talking before. So if you start asking these questions and you start looking at some of the things we use and the decisions we make, it takes on a different light. Now, I'm not going to claim I'm Copernicus because I don't want to be imprisoned or the like, but hopefully maybe some of you can begin to think about things a little bit differently of how we work in the field and ask some of these questions? I would say it goes back to definitions. So if we don't know how to define security, we can't measure it. And if we can't measure it, we can't know if we're improving it. So what do? We use the things we can measure. We can measure cost. We've got the invoices, we've got the bank accounts, we can measure cost in whatever currency we're using. We can measure speed because we've got the tools to measure speed. We can measure time to change, which is a speed kind of issue. We can measure lines of code. And we use those as the metrics, but none of those is measuring security. And none of those is really measuring any issue of quality. So it all goes back to the fact that we don't know what it is we're doing, so we measure whatever's available. There's an old joke that some of you may have heard about the policeman who's walking the beat comes upon a drunk individual on his hands and knees searching the sidewalk, and the policeman says, what are you doing? And he said, I lost my keys, I'm looking for my keys. So the policeman starts looking, and some bystanders start looking, they're looking all over. And after a while, the policeman says, are you sure you lost your keys here? He goes, no, I lost them across the street, but the light's better over here. That's effectively what we're doing as an industry. The light's better over here, and so that's where we're focusing our attention. I think we can change. And we can change by increasing awareness, by rethinking the conventional wisdom of these things that we take for granted, by seeking simplicity instead of adding on new features, is thinking maybe for every new feature you add, think about one you can get rid of. For every new security tool you add, is there one you can get rid of instead of just having new layers? Thinking about whole systems that includes people rather than excluding them. And, of course, by promoting good values that underlie all of these. We can do it as a community. If you're interested in learning more, this is the cover of the book. We have 175 myths and misconceptions. So if you resonated with any of these, you may find more here. Then again, you may not. But if you like it, buy a few hundred copies for your friends. But truly, I think we have to step back if we're going to mature as a field and start thinking about some of the things that we have gotten wrong, that we've come to believe because we've been an insular community operating without some of the formalisms. That isn't a condemnation, right? When we look at chemistry, its original origins where people didn't understand, they were looking for the philosopher's stone to turn iron into gold. And they learned a lot of things along the way. And when we look at medicine, they didn't understand a lot about biology, and they were thinking about the four humors. And they used bloodletting, for instance, as a cure for some things. They killed more than they helped, but nonetheless, they were learning. They had some explanations that they were trying to use as a model. We've been doing that for a while, and it's time that we actually sort of step back and said, are we doing the things that help us, or are we going to change the way we look at things to make things better? And with that, I will conclude and thank you all for your attention. I don't know if I have some time left for answering any questions or comments. I think I do. So I've got about 10 minutes left here. If anybody either wants to tell me that I haven't had enough coffee, or any observations or questions any of you might have. I'll also say one or two of you have caught up. My wife and I will both be happy to autograph a book if you've got one, preferably one of these books, but just anything that we can put a pen to. Yeah?
Before I ask my question, I would like to apologize personally for the text being so long.
Oh.
And my question is, this is probably something adjacent to Courtney's third law. It's a management problem which can lead to huge technical problems, and that is insider threats. I'd like to hear your thoughts on those as well.
Okay, so the comment or question, it's a little of both, is that there are some management approaches that create technical threats, and particularly insider threats. And what are my comments on insider threats? That's a complex issue, and there are partial solutions. One is to realize we will never be able to prevent all insider threat. Every insider who suffered a personal failing or has a problem may have been trusted before that occurred. Some insiders actually have the intent to cause harm, and we can often weed those out through careful vetting of background and otherwise. But it is a truth that there is a percentage of people who will develop emotional or mental issues, especially under stress, some disease, and we can't anticipate those. They may be valued employees up to that point. So what we have to do is we have to have a combination of mechanisms in place for observation and for peer support and reporting. What's been found for a vast number of insider problems, and you hear it not only in computing but out in the real world, where people will go, well, he was acting kind of oddly, but we were afraid to say anything. We need to be in an environment, again, where our users are empowered to know if they see something suspicious that they aren't going to get in trouble and who they're talking to isn't going to get in trouble if they're not doing something wrong. Simply awareness of the potential for insider threat also makes a difference. Doing things like least privilege, partitioning of privilege. I won't say zero trust because zero trust is nonsense, but and any of you who want to fight about that, I'll be happy to do. If you have zero trust, you don't use the system at all because you don't trust it. I mean, that's the simplest reduction. So it is a complex problem, but that we will never solve like any of the other issues, but we can do a better job at supporting people. And another aspect of this, for instance, is if somebody is encountering difficulty in their personal lives, and we all have that at some point, unless we're terribly, terribly fortunate, and it gets reported or noticed by a supervisor or by someone, those are individuals we should have mechanisms within the organization to support. So we should be able to support them in recovery if they're a valuable employee, rather than penalizing them at a point where they're already having problems, because that leads to resentment, that leads to other kinds of problems. So that's a little long answer, but it's an interesting topic to explore.
Thank you very much.
You're welcome. Anybody else? Yes, sir.
I actually have a question. So that was interesting, your comment on zero trust. So the way sometimes I see things is we get buzzwords in the industry. They're trying to explain something. How do you think that affects and adds to the hype of some of the things having new technology and these things like that? How does that distort the base view and the fundamentals that we try to do?
It's a great question, and the question is, in this industry, we see a lot of buzzwords that show up like zero trust, and it distorts some of our view of things. How do we deal with that? Was that an accurate summation? When you're reading trade publications, when you're visiting vendor displays, they're all trying to differentiate themselves from each other. And so someone who can come up with a new term or a new technology that they use, right? So threat intelligence was a buzzword a while back, or extrusion protection was one that had a brief time that was available. We see that on a regular basis because they're trying to differentiate themselves from each other. And a common approach in advertising is, if you define what you're best at, because you're the one who defined it, you can always claim you were number one or in the field, or the first or the best. And then the buying public very often falls for that, because we don't stop and ask, well, is that even an important property? How do you measure that? Who's made the determination? So we need to be aware of those kinds of manipulations. We talk about several of them in the book, where we sort of fall for novelty, or we fall for crowd-based approaches, which are not necessarily based on any kind of sound evaluation. It is a difficult problem because as human beings, we have this set of biases towards We want the best, we want the newest, and we want what the majority have. That's why 4 out of 5 dentists recommended toothpaste. Well, why did they recommend it? Well, they may have been paid to recommend it, and that's why only 1 of the 5 was honest enough to reject the payment. We don't ask those questions. What is the recommendation based on, or where did you find them? We need to be more critical as consumers in thinking about what is being advertised and told to us. One of the things in the book we talk about, and I mentioned, keep in mind, and this is not intended as disrespectful for any of the vendors that are out here or any of you who are associated with a company, but no company is built on the premise of protecting you. None. They are built on the premise they're going to make money. And so their products are being sold to you, some with good faith to try to solve a problem, others with a realization that, well, maybe it doesn't solve all the problems. And in fact, most things that are sold to you with a default configuration that reduces the number of calls you have to make to tech support because that costs them money. So again, you need to be discerning as consumers to sort of understand really what it is that you're getting and what are the terms about. I hope that answered your question. Okay. There was another question back here somewhere? Yes, sir.
So my impression is that we're an industry that's guided by policies. And as technicians and in our background in computing, we tend to think binary. It either applies policy and it's acceptable or it's against policy. How can we translate that and quantify it in a way that shows empathy towards our users?
Great question. And to summarize, technologists, we tend to think in binary 0-1 terms because that's our background. But that isn't necessarily how the world works. How do we transition into something where we can support users and, not a term you use, but some of the gray areas and the areas in between? Excuse me. It's dialogue. As the people who are expert in the technology, we need to be having more conversation with the policymakers in not only our organizations, but society at large, to talk about what is possible, what isn't possible, and what are the goals. Because very often the people who are setting the policies don't understand what the technology is available to do, and the technologists don't understand the underlying policies and issues. I believe that cybersecurity as a discipline is more than computing. It includes things like social psychology, law, ethics, and we need to be educating the next generation in those topics as well. But it is a dialogue issue that we're going to have rather than us just coding something. So right now we are having at least 2 major public policy discussions in various parts of the world. One is, for instance, on whether or not to allow end-to-end encryption that can't be broken by law enforcement. And that comes back about every 10 years. So 20, 30 years ago, it was we want to stop the terrorists, then we want to stop the drug dealers, and now we want to stop the child pornography purveyors. I don't know what it'll be in 10 years from now, but that keeps coming back, and technologically we can't do that and also maintain the safety guarantees we want. That discussion has to be a little bit more robust. And there's a really big conference going on right now in England about how to regulate AI and ML. And that also is an area where we have to have technologists talking about what's possible with the policymakers about what it is they want to achieve as goals. As technologists, we shouldn't be setting all those goals, and the policymakers shouldn't be the ones dictating the technology. It should be a collaborative effort. Other comments or questions? Yes? The CIS benchmarks and scoring tools? Okay. I think it's a good start, but very similar to, for instance, taking the cybersecurity framework and doing check marks against it. What we're doing is we're measuring implementation rather than fundamental properties. It's a good, I'm a firm believer in checklists. For instance, in medicine and aviation, they've discovered those are really important. Generally, the experienced pilots who continue to live to pilot planes use checklists. Those of us in cybersecurity who want to continue to have good results, we should be using checklists to help manage the complexity. But checklists only measure against certain implementations. They don't talk about fundamental properties. Okay, well, not seeing any other hands up. I will be here at least through lunch. If you want to catch me in passing and render some comment, I'd be happy to further converse with you. And it's great to be back in Rochester. Thank you very much for inviting me, and enjoy the remainder of the conference.